Hello and welcome to another video. This time I'm just going to take you through sketching log and exponential graphs, and I'm also going to do a bit of modeling. Now, I'd like to point out with a modeling topic, it's just as likely to come up in the stats section of the course, so in the applied exam, as it is in the pure exam. So do bear that in mind. It can actually come up in either. But anyway, let's just talk about sketching basic log and exponential curves. Um, Might as well do exponentials first, I guess. So, okay, we'll draw a little graph. Hopefully you know, oh, my axes are upside down, sorry. Hopefully you know exactly what natural log of x and e to the x look like. Actually, you don't have to use natural log and e there. It would work with anything of the form y equals a to the x. So this is what all curves, provided a is bigger than 1, this is what all exponential curves will look like. It will increase exponentially. It will go up and up and up. And when x is 0, you get a to the power of 0, which is in fact 1. Watch out for that. That can definitely catch people out. And that is what y equals e to the power of x looks like. Now, I've called it a to the power of x because it's exactly the same as what 2 to the power of x, 3 to the power of x, 5 to the power of x. They're not exactly the same, but they're all going to be slightly different curves, increasing at a slightly different rate. So, maybe, I don't know, maybe if the black one is 2 to the power of x, then 3 to the power of x is just going to be a little bit steeper. So maybe it goes a little bit more like that or something like that. Sorry, it's not very neat, but that's just giving you an idea. Anything of the form y equals a to the power of x is going to be of this format. Now, what's the opposite of this graph? Well, the opposite is the inverse. And for inverse graphs, for inverse functions, when you represent them graphically, they're always a reflection in the line y equals x. So I thought I'd quickly draw the graph y equals x, the line y equals x on there. And now I can kind of anticipate what y equals log base a of x is going to look like. It will be exactly the same, but it'll be going like that, and it'll be going through 1 on the x-axis because that's x and that's y. So this is the curve y equals log base a of x, yeah? They're opposites, they really are. Now, think of it with e to the x and natural log of x, because natural log of x is just log base e of x. This works basically for all cases, provided a is bigger than 1. This is what those two curves will look like. If you know those first two curves, then you can actually do a variety of different curves and shapes, just using function transformation principles. So, okay, let's take a few examples of those. Let's say you were asked to sketch, let's do a few examples. Sketch y equals e to the x minus 2 up there and then plus 1 down here. Yeah? Well, it's not too difficult if you start with e to the x. Now remember, e to the x looks just like, oh, need a longer one than that. E to the x looks just like the a to the x graph over there. It's exactly the same. But this is a function transformation. And essentially, we've gone from, if e to the x, if we think of this as your f of x, if we think of e to the x as your f of x, how has it changed? Well, it's become f of x minus 2 and then add 1 on the end. Yeah, that's how we get from e to the x all the way over to e to the x minus 2 plus 1. That represents a function transformation where you move it 2 to the right and 1 up. So we just need to move this curve 2 to the right and 1 up. And it's difficult to show that we've moved it 2 to the right and 1 up. But what we could do is give the new y-intercept. Now, to work out a new y-intercept, all you've got to do is let x equal 0, and you'll see it's at e to the minus 2 plus 1. Oh, one thing I haven't shown on this curve, and I should have, sorry, let me just get the curve back, is that now, rather than the asymptote being the x-axis, the asymptote is now going to be on the line y equals 1, because this can never be smaller than y equals 1. It's always bigger than y equals 1, because this part of the function is strictly positive, and after you're adding 1 to it, well, it's going to be strictly greater than 1. And so you'd end up with a curve which looks something like that. Now, it's always nice to put the intercepts on, and if you let x equal 0, you can see the y-intercept is going to be at e to the minus 2 plus 1. But you should also put on the asymptotes for any curve sketching, particularly with log and exponential graphs, because they're often vertical or horizontal asymptotes. Let's do one kind of similar to that. Let's do one but with logs. So what about if we had, I don't know, let's do one where we have to do a little bit of fiddling around. Y equals natural log of x squared. Oh, actually, no, let's make it a little bit more complicated. I'm making this up off the top of my head, as you can see. Natural log of x minus 2 squared. If they asked me to sketch that, I would possibly be a little bit worried first until I'd taken that power down. Because then I can see that if, rather in my last example where we were starting with e to the x, let's start with natural log of x. That's your function of x, if you like. How have we got to this stage? Well, we're doing 2f of x minus 2. So we need to move it 2 to the right, and then we need to stretch it by a scale factor of 2 in the y direction. And we're dealing with log base a of x this time, or natural log of x this time. So once again, let's draw out our graph. Well, if we're moving the log graph 2 to the right, the stretch we can't really show, but before it had a vertical asymptote at x equals 0, in other words, the y-axis. Now it's going to have an asymptote at x equals 2. Rather than going through 1, it's going to go through 3. And the stretch, okay, you can kind of stretch the gradient a little bit, but it's pretty hard to show. But you can see it should go through 3, because when x is 3, you get 3 minus 2 is 1, and natural log of 1 is 0. So when x is 3, y is 0. And you've sketched it. Okay, that was just a little bit of graph sketching which I wanted to talk about. The second thing I want to discuss, which is kind of different, it's a different kind of question anyway, and I'm going to pop it on the page. This is a log question from, I can't remember where I'm trying to, sorry, struggling with the IT here, struggling with the IT. I tell you what, I'm going to place it there, and I'm going to zoom in. That would probably be the best idea. There we go. God, I really struggled with that. Okay, so this is a question, I think it's from the sample paper, and it's on log modelling. Now, like I say, it can come up on stats or on pure, but let's have a look at what we've got here then. So we've got a town's population, P, modelled by the equation P equals AB to the T, and naturally, population proceeds exponentially. Yeah, you tend to get exponential growth in population. One of the reasons why they're worried about, sustainable development at the moment. But here's axis. Now this massively confuses people, particularly in the press. If they ever produce log graphs, you can understand what it's really saying. A log graph is a bit like the Richter scale for earthquakes. It's not a linear scale. It's an exponential scale essentially. And what it means is it turns an exponential function into a straight line. Anyway, let's get into the guts of the question here. So we've got that general equation for the population, but bear in mind the graph is showing log p against t. Now, the first thing it wants us to do is it says the line L meets the vertical axis at 0.5 as shown, and the gradient of L is 1 over 200. Write down an equation for L. Now bear in mind, whenever it says write down in a maths exam, it means it should be obvious, yeah? Now, normally we would use y equals mx plus c for a straight line, but here y is log p. Yeah, and I think it's base 10, and for some paranoid reason they've written down the little number 10 over 200 plus, and then where does it hit the y-axis? I believe it's at 5, so I can just put plus 5 on the end. That's what they want for that part of the question. Yeah, they don't want p in terms of t, they want log p in terms of t. That's why it was only a 2-mark question, because it's quite easy. Now, how does this tie in to finding the value of a and b? Well, if we go back to this equation, p base 10 of both sides, we get log p equals log of a, b to the t. So I can say that log p equals log a plus log b to the t, and therefore log p equals log a plus t log b. Now that step always works the same way. It really does. And you'll probably start shortcutting some of the steps there because it's it's always works the same way and it's pretty quick to do. Careful that you don't pull that power down before you've applied the log A plus log B log law. That's one common mistake I see, and that is wrong if you do that. Otherwise there'll be T on both of them and it's absolutely incorrect. And it's because of BibMaths really. But okay, it's because it's not AB all to the T, it's A times B to the T. Yeah, so that's why you need to do that first. Okay, now compare this. This is supposed to be the same as this one. Well, it's looking good so far, but then we get, if I write in a slightly different order, T log B plus log A. Oh, great. Okay. Oh, did I plug in my C? I didn't plug in my C as 5, did I? I do apologise. I don't know why I didn't do that. That is definitely a mistake, and I will be marked down for it in the exam. Plus 5, because the Y-intercept was 5. Okay, I can now just using inspection and eyesight really see that, okay, I can now find the value of A and B. And these questions always work the same way, so you do get used to these. Log B must be 1 over 200. And let's do it in a different colour. Log A must be 5. Now, how do we undo logarithms? Well, remember, let's go back to black for a second. Okay, log base 3 of 81. I always quote this fact because I always remember that 3 to the power of 4 is 81. That demonstrates how you get rid of a logarithm. That to the power of that is that. And remember, these have both got a little invisible 10 in there, which we don't always write down if we don't want to, if it's base 10. And so what I can say at this point is that B equals 10 to the power of 1 over 200. Yeah. That to the power of that is that. And A equals, oh, let's use the right, could be very big. That means that B is 1.011579. I'm going to use quite a few decimal places there as well, because I think it will mess things up if I do use these for modelling later on, which you often have to do. And A is obviously a 1 with 5 zeros after it. 1, 2, what is that, 100,000. Okay, and we've got the value of A and we've got the value of B. Okay, so far so good. Now, I do have another part of this question. Let me just bring it in. Hope messing everything up. Place image. Yeah, here we go. So, interpret. That is such a key word which students ignore in maths. I promise you, whenever they say interpret, they will mean make a comment which relates to the context of the question. In other words, they want you to go back and talk about the foundation. So, what does it mean to say that population is growing at a rate which is 100,000 times by 1.011579 to the power of t? You might think, what am I writing that down for? Where am I getting that? Well, that was from the start, like AB to the t. So I've written it down like that, yeah? Now, we've got to interpret what A and B actually represent. Well, A is this figure, and it actually represents initial population, because when t is 0, that becomes just 1, and you get P. Experiment or the model, should I say. What is B? Well, B is the rate of growth, yeah? Now, what do I mean by rate of growth? I mean, basically, every year the population is getting, what is that, 1.1579% larger? That's what we're doing, yeah? B is the rate of growth, and I'd actually interpret it as well. I'd say it's the rate of growth, i.e., every year the population grows by, 1.1579%. Yeah, that's what it's telling you. That's the rate of population growth. And you can see this model's quite, it sounds quite sensible anyway. A national population of 100,000, it's growing at 1.1579% a year. Sounds about right. Okay, now let's do part D, part 1 and part 2. These will be quite straightforward, I think. So let's have a look. Oh, I didn't realise that would rub out the question. Okay, let's just go down here. Okay, so let's do part D. Okay, find. We're now got to use these numbers. The population predicted by the model when t is 100. So we've got 100,000 times by 1.011579 to the power of 100, because t is 100. I'm just going to do that on a calculator, obviously. 100 times by 1.011579 to the power of 100. Okay, I'm getting a population of 316,213. And I might write roughly equal, and actually it's slightly above the 0.5, it's 0.5658. So I'll round it up to the nearest person here because it represents population, and it did want the population predicted by the model. So there we go, I'm going to do that. You probably would get away with it if you didn't if you didn't round to an integer, but you never know. Seems like a sensible thing to do to me. Okay, the number of years it takes for the population to reach 200,000 according to the model. So this is just the other way round kind of thing. 200,000 equals 100,000 times by 1.011579 to the power of t, and we're finding t this time, 1.011579 to the t. Now, how do we solve an equation like this where we're looking for a power? Well, that's what logs are for. You'll probably do it a different way to me. I do it like the old way. I just take logs, base whatever you like really, of both sides, and I bring the power down, and therefore t is log 2 over log 1.011579, and that comes to, let's have a look. You've probably got your own way of doing this. That's cool. Where's my log button on my calculator? Oh, they're all mixed bases now. I'm a dinosaur now. 0.11579. Okay, I'm getting 60.2, and I think t is in years, so 60.2 years. Okay, so there we go. That's the number of years it takes for the population to reach 200,000, according to the model. State two reasons why this may not be a realistic population model. Okay, I'm going to give you a couple of reasons which I would accept. My first reason would be, for this model, population will always increase. This model will only ever show increasing population. But physical constraints are likely, but all populations are subject to physical constraints. Do you know what I mean? Like how much water there is available, how much food there is available, etc., etc., etc. But all populations are subject to physical constraints. So that's my first reason. So I'm basically saying it's going to eventually give you like infinite population. Subject to physical constraints. My second reason, and I think I'll just explain this because I'm getting bored of writing it down. My second criticism is that it assumes the rate of population never changes. It's always 1.011579%. Yeah, like these are reasonable assumptions to make, but like they're not realistic. They're really not realistic. That's not going to be the case in real life. And models get better and better and better the more you build in and incorporate into your model all kind of tiny little eventualities. But yeah, that's all you really need. You know, it assumes a fixed rate of growth. That's what I would criticize it for. Okay, I hope that makes sense. I hope that's helped you, and best of luck with your revision. Well done.